You are listening to EE Times On Air, and this is EE Times Current. I'm Eric Singer. Today's podcast is sponsored by Synopsys. Our technology, your innovation. The semiconductor industry is undergoing a shift with the rapid adoption of multi-die design, driven by that promise of improved power, performance, and area that we hear of as PPA. But with that innovation comes complexity, and one of the biggest challenges is ensuring silicon reliability and health through effective multi-die testing. In this episode, we dive deep into the world of multi-die design for test, what it means, how it differs from traditional monolithic design testing, and why it's critical for the future of semiconductor manufacturing. We'll learn how testing spans from individual dies to multiple dies to die-to-die links, and why silicon data is essential for maintaining multi-die health during both manufacturing and in-field operations. We'll explore the future of multi-die design for test and discuss Silicon Lifecycle Management strategies that designers can implement today to stay ahead. Our guest today is Faisal Ghoriawala. He's the Principal Product Manager for multi-die test-related SLM products at Synopsys. With over 2 decades of experience in the semiconductor industry, he's specialized in embedded memories, logic and I/O libraries, NVM, and DFT. Faisal began his engineering career at ARM, Artisan Components, before transitioning to business development and product management roles at Synopsys. He holds a Master of Science degree in Electrical and Computer Engineering from North Carolina State University and a Bachelor of Engineering degree in Electrical Engineering from Sardar Patel College of Engineering in Mumbai, India. Thanks so much for joining us today, Faisal.
Well, thank you so much for having me, Eric.
So let's start by just establishing some ground basis knowledge here. What is multi-die testing?
Yeah, sure. Let's perhaps start with defining what is multi-die. So multi-die refers to scenarios such as 2.5D, where heterogeneous or homogeneous individual dies may be connected via substrate or RDL, redistribution layer, some sort of silicon interposer or bridge, or through 3D IC, where dies are directly stacked on top of each other via hybrid bonding. Both scenarios may exist concurrently in more complex multi-die packages. So multi-die test or chiplet-based testing then refers to the functions associated with multi-level test, repair, debug, and diagnosis that needs to be planned at least 3 different stages. That's at the individual die level or intra-die, between the dies or inter-dies using the die-to-die interconnect, and finally at the package level during final test. Another way to look at this, in addition to individual die, multi-die testing needs to consider substrate or interposer related testing, hybrid bond and or microbump testing, and finally assembly testing. So this now gives rise to known good die or KGD, known good stack KGS, and finally known good package or KGP concepts. Now, just like monolithic die testing, the goal is to identify defects early. The difference for multi-die testing is that the user needs to ensure that only known good parts are assembled to minimize debug and or prevent costly field failure subsequently.
Yeah, there's such a degree of complexity here on so many levels.
Right.
And obviously, just slapping together all the known good dies isn't enough. We've got so many more constraints here, and we need a more holistic approach, right? Something from silicon to software. And especially with the rise of AI, autonomous vehicles, high-performance data centers, multi-die is clearly the future of where we need to go as an industry.
Mm-hmm.
So I'd like to ask you just to expand a bit more on how multi-die testing is different from the traditional test for monolithic structures.
Yes, absolutely. While traditional monolithic testing is quite well understood, if you look at conventional 2D IC testing, which has some digital and analog content, then these ICs will have their own dedicated test only pads, resulting in a dedicated JTAG or IEEE 1149.1 TAP interface to the outside world for production manufacturing test purposes. Now, for multi die, individual dies or chiplets in the stack may not all have direct access via their own dedicated JTAG. So often you'll find that only the bottom die or the main die may have a JTAG mechanism, and all the other chiplets are forced to reuse that via some mechanism. Another key difference between the two is the need for testing the die to die interconnect for chiplet based designs that is not applicable for monolithic designs. Depending on the type and the speed of the interface, for example, you could have a 100, 150 megahertz GPIO based die to die connectivity, or you could have a UCIe based die to die phi to phi communication running at 40 gigabits per second. The requirements and implications for testing can vary widely. This will, of course, also influence the diagnosis and repair methodologies that the user needs to deploy in this environment. So, unlike monolithic scenarios, multi level testing is typically performed at three stages: pre bond or wafer level testing, mid bond, and finally post bond at package level.
When you mentioned the IEEE standard and the difference between monolithic testing and multi-die testing,
Mhm.
monolithic testing obviously been around for a while. We've got standards in place. Let's talk a little bit about what is the state of the industry regarding a standard for multi-die testing, and how important do you see those standards playing a role in multi-die testing?
Right. So, indeed, there is a confusing array of options in multi die designs and packaging. And having standardization helps reduce cost, lower risk, and improve time to market for designers. There are, as you mentioned, several relevant standards here, and they build on those relevant to monolithic IC testing, such as IEEE 1149.1 and IEEE 1500, which have been there for many, many years now. The first of the relatively newer standards is IEEE 1838 that standardizes multi-die and chiplet-based DFT access. So IEEE 1838 enables access to DFT, functional safety, security, debug, and Silicon Lifecycle Management features, including scan, compression, logic built-in self-test, memory BIST and repair sensors, and so on. This standard defines die level features that, when compliant dies are brought together in a stack, comprise a stack level architecture that enables transportation of control and data signals. The serial test access mechanism defined by IEEE 1838 is mandatory. IEEE 1838 compliant dies must have a primary test access port called as PTAP on their primary interface. The PTAP is very similar to the TAP in IEEE 1149.1. For each secondary interface of a compliant die, we now add a secondary tap or an S tap as well. IEEE 1838 mandates a die wrapper register or DWR with which one can perform an interconnect test. An optional element of IEEE 1838 is a user configurable flexible parallel port or FPP, which provides a high bandwidth path for transporting larger volumes of data up and down the stack. This might be used to add more parallel scan chains, for example. You can think of FPP as an elevator going up and down the IC stack, carrying the ATPG related information. Another emerging standard, which is still in draft stage, is the IEEE P3405. This has several fronts on which is it is trying to address, an architecture supporting test and repair of interface lanes, and a language to support that effort. With the goal of reducing implementation costs, designers would no longer need to customize their interface test and repair infrastructure if EDA tools are available to automate that portion of the design process. In addition, P3405 could create a uniform mechanism by which the test and repair data flows between interfaces, test infrastructure, and ATE or automated test equipment, making it easier to support interfaces of various types and from disparate suppliers.
You brought up Silicon Lifecycle Management early in that response, and I'd love for you to expand a bit on how SLM and multi-die testing are related.
That's a good question. Silicon lifecycle management has become even more important in multi-die context because of the synergies in leading application markets driving silicon health and safety. With the increasing emphasis on improving reliability in these markets, testing is no longer relegated to production manufacturing alone. Power on self test or post, in field test during scheduled downtime, mission mode testing, that is, testing during functional mode, and even periodic testing at regular intervals are now increasingly common requirements for applications demanding compliance to standards such as ISO 26262 for automotive. Silicon reliability is key even for markets such as data center. As an example, you can think of LLM, large language models training on servers in the data center. These runs can take many days or even weeks at a time. An unanticipated failure or downtime in the system hardware or link can result in a significant loss of productivity and increased costs. In this context, using SLM to test the die to die UCIe connectivity between the compute chiplet, accelerator chiplet, and IO chiplet in field to determine any marginality in the link during a scheduled downtime in advance would therefore be quite valuable and desirable. So, successful multi die test requires a rigorous application of silicon lifecycle management concepts.
You've given us a really fantastic overview of where we are today, what the standards are, what the relationship is between SLM and multi-die testing. I'd love to now turn our eyes towards the future. In terms of multi-die SLM, what do you think the vision is moving forward?
So, optimal multi die silicon cost, quality, health, and performance can only be achieved through continuous in chip monitoring, test, and analytics. There are various environmental, structural, and functional monitors that can enable deep insights from SoC manufacturing to in field systems. Meaningful data is gathered at every opportunity for continuous analysis and actionable user feedback. Multi-die design must account for different types of interfaces between the dies. These can be logic to memory, like HBM, or logic to logic, such as high-speed GPIO, or high clock rate specialty interconnect, or even high bandwidth die-to-die PHY, such as UCI. SLM approach to multi-die design then warrants a deep understanding of the test challenges associated with these interfaces and how to address them during the design, ramp, production, and in-field phases in an efficient manner. Pre-configured test, monitoring, and repair SLM logic can perform these functions with high quality and test coverage due to their programmable and algorithmic nature. User expectation would be that this SLM logic work closely with or have an established methodology EDA tool flow to ensure appropriate configuration, generation, insertion, and validation of this SLM IP in the design environment. By means of SLM software, the user should be able to perform any post silicon debug and diagnostics during ramp and production test And this could mean traversing the multi die hierarchy to identify the physical, not just the logical, failing XY coordinates deep within a specific die within the package. Finally, SLM in chip or cloud based analytics can be used for predictive maintenance, aging identification, and fault detection, thereby mitigating the risk of catastrophic system failures and increasing overall system reliability.
That's actually the perfect segue into what I'd like to talk about next, which is the overall ecosystem. How important is that multi die ecosystem? And I would love it if you could give us an example of a success story that you've heard of or with a customer or partner that you've worked with.
Sure. The ecosystem enablement in terms of multi die is particularly important. And not just because there are dozens of permutations, combinations of interposer, stacking, architecture, package, chiplet, and die to die interface options. Not all these combinations have necessarily been deployed on silicon, thus creating some interesting choices for the SoC designer. The key is successfully deploying all these individual variables together in a fully integrated solution while managing all the time to market pressures and risk to first time silicon. One such example of ecosystem is how Synopsys worked closely with TSMC as a leading foundry. In 2023, Synopsys and TSMC started work on a joint multi-die 2.5D demo test vehicle to demonstrate how Synopsys TestMax tools and Silicon Lifecycle Management solutions can be used in conjunction with TSMC's advanced CoWoS, that is, chip on wafer on substrate packaging technology. The goal was to demonstrate multi die reference flow methodology to enable monitoring, test, debug, and repair across the silicon lifecycle, showing no loss of coverage or pattern inflation when targeting dies in a stack. Two configurations were deployed. The first was a die to die communication via high speed UCIe PHY with the SLM monitor, test, and repair IP. And the second was a die to die communication using GPIO to leverage the IEEE 1838 standard. Both configurations support full execution of test, monitor, debug, and repair capabilities utilizing on chip resources for Synopsys UCIe PHY IP. Objective is to demonstrate comprehensive silicon lifecycle management deployed across pre-born, post-born manufacturing stages, as well as in-field power on stage and mission mode use case scenarios. Starting at ITC, the International Test Conference in 2023, the preliminary results were published as an IEEE paper. As we made progress on developing this important proof point, interim results have been published in several industry conferences such as Synopsys SNUG, the TSMC Symposium, and the Chiplet Summit since. This activity finally culminated in a successful two chiplet and interposer tapeout in late 2024, the results of which were published and shared during the keynote of the 2025 TSMC Symposium recently. Designers can use these results to increase their confidence with silicon proven high quality multi die reference solutions as they navigate their choices of foundry, EDA, and IP providers. If I may, I would also like to reference a recent Synopsys and end customer success story with the ASIC provider Socionext. Socionext was developing their first ultra large scale HBM based multi die SoC, targeting the AI and HPC applications, Eric, that you talked about for the multi terabyte per second memory bandwidth needs. Their architecture was based on a logic chiplet with four HBM modules. However, with a total of 6,800 HBI signal connections, that is 1,700
Wow.
per HBM module, yeah, and that too with very narrow pitch, it was not feasible for them to test these via ATE or conventional single die methods. While the HBM standard itself includes the ability to test and lane repair failed HBI connections, Socionext needed the ability to automate the complete test flow at different stages during wafer test and final assembly. The Synopsys SLM solutions for multi-die, such as the Star Hierarchical System or SHS and EXT-RAM, help Socionext test the HBM5, perform the HBI connection test and repair, and finally perform the HBM DRAM test, which is at post-assembly final test with high quality due to programmable algorithmic capabilities. The collaborative team effort developed a strategy for bottom up construction and validation of different test scenarios needed at each stage. We have the detailed story available on the Synopsys website. So, what was the final result out of this? Socionext was delighted with eventually achieving their target memory data rate of 3.6 gigabits per second while shipping their product on schedule and without any impact on their logic die size.
Wow, the story you related about Socionext and the results you were able to get was a fantastic example. And I also really appreciate hearing about how Synopsys and TSMC collaborated to take advantage of the standards that are still really in their infancy here.
Sure. So Synopsys has been investing heavily in the IP, EDA, and SLM products to offer proven, low risk, and complete solutions so that so as to increase confidence for our multi-die designers. The Synopsys multi-die solutions enable early architecture exploration, rapid software development and system validation, efficient die-to-package co-design and optimization, robust die-to-die and chip-to-chip connectivity, and improved manufacturing and reliability for end users. The Synopsys TestMax family of products offers a highly configurable test automation flow based on the shift left idea. These include early testability analysis and planning, hierarchical ATPG compression, physically aware diagnosis, logic based memory self test and repair, and analog fault simulation. A key element includes a die and stack level testing support with IEEE 1838 standard. The collaboration with TSMC on multi-die demo vehicle was actually a proof point of this work. The TestMax ATPG and diagnosis flow can extract die-to-die and interposer bridging defects, for example, and generate the necessary ATPG patterns for diagnosis. The Synopsys SLM portfolio provides different types of environmental, structural, and functional silicon monitors with cloud and edge analytics solutions. Coupled closely with the TestMax products, the SLM portfolio offers insights from design to in-field, meeting design, test, and operational goals for entire lifespan of a system. Related to multi-die test, Synopsys offers a programmable high-quality external DRAM and interconnect-based test engine called as EXT-RAM or external RAM, a monitor test and repair engine for UCIe PHYs, referred to as UCIe MTR, a lane test and repair engine or LTR for high speed interconnect with redundancy. All these engines work closely with Synopsys Star hierarchical system that acts as the overall DFX network on chip. Roadmap support for the latest HBM4 standard, latest UCIe Gen 2 PHYs support are some of the activities that are eagerly awaited by our SLM users. New capability additions relevant to multi-die are ongoing for both Synopsys TestMax and SLM portfolios. Finally, Synopsys continues to collaborate closely with foundry partners, OSAT providers, and others across the ecosystem for users to realize a multi-die vision of scalability, fast time to market with reduced cost.
The key word that I heard you say in that response was confidence. And I think when you talk about validation, optimization, the need to shift left and catch things earlier in the process, this really paints a picture of a very holistic view that Synopsys is taking here. And You touched on a few things in that answer that I think listeners are going to be interested in hearing more about. So we will post links in the show notes of this episode so that folks can go to the Synopsys site to dig a little deeper on so many of the issues that you just mentioned, because I think they're all critically important for all future-looking designers these days. So, Faisal, I can't thank you enough for sharing everything that you've learned over the last 2 decades, really, and particularly the innovative things that you and the rest of the Synopsys team are doing along with your partners in this field. Thank you so much for joining us.
My pleasure, and thank you very much for having me here.
That brings another episode of EE Times Current to its end. Thank you for listening, and thanks again to our guest, Faisal Ghoriawala, for joining us. EE Times Current is available through the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find a transcript along with direct links to the other stories we've mentioned and other resources. EE Times Current is produced by EE Times. It was engineered by Taylor Marvin at Coop Studios. I'm Eric Singer. Thanks for listening.